All right, in section 7.2, what we're going to be doing is something that has to do with applications of the normal distribution. We're going to find and interpret the area under a normal curve. We're going to be doing this with a set of values that we have learned before. We have found the z-score before. If you don't remember that, I'll remind you in this lesson. But our z-score corresponds to a table that you have in the very back of your book that is found in kind of like the cardboard fold in the back of your book. It's called Table 5, and we will be using that table to help us in finding our z-score values, okay? So let's look at some applications here. So our first objective in this lesson, we're going to find and interpret the area under the normal curve. So standardizing a normal random variable, this is how we do it. Suppose that a random variable x is normally distributed with the mean and standard deviation given. Then the random variable, we can find our z-score, and this is normally distributed with the mean of 0 and standard deviation of 1. The random variable z is said to have a standard normal distribution. So the z-scores that we have found before in the past are going to help us in calculating probabilities and such in this chapter here. So the table that I was referring to gives us the area under the standard normal curve for values to the left of a specific z-score or z-value that you have found. So like you see in this figure, we will find the z-value for certain data given to us, and then the area to the left of that underneath the curve of that normally distributed information that we have is known as the probability of that information happening. So we'll go over it some more. It's hard to explain without given a set of data. So as we are given that, you'll probably understand a little bit more than just this graph right here. Okay, so let's look into it some more. So I give you this little example right here. It says an IQ score can be modeled by a normal distribution with our mean equaling 100 and a standard deviation of 15. An individual whose IQ score is 120 is 1.33 standard deviations above the mean, which is calculated in this way. We use our z-score to help us in calculating that value there. So 1.33 standard deviations above the mean, we're going to use that 1.33 to help us in finding the probability of sorts. So here's how you use the z-table that you have in the back of your book. It says the area under the standard normal curve to the left of z equals 1.33 is 0.9082, and this is how you find it. The first two numbers here, the 1.3, you look down in this column right here and you find it. The third number, the 0.03, this number right here, you find it along the top here, and that row and column match up to this value right here. And that right there is our probability of a person who has an IQ of 120. So it is very likely for a person to have an IQ of 120. It is according to this right here, 0.9082. Okay, so there's several people in the population that actually have that same IQ right there. All right, so let's take another look at another example. All right, and if we are looking for people who score above 120, this is how we are going to use that. Since we know the z-score, 1.33, and we have found the probability or the area under the curve for that particular z-score is this right here. To find the rest of this area, the area to the right of this whole shaded region, we use the complement rule. We're going to say since this whole normal curve, the area under it is 1, then we're going to take 1 and subtract this area that we know to be left of our z-score to figure out the area under the curve to the right of the z-score. So that is how you find that particular area. So in a z-score table, thing you have to remember about it is once you find your z-score for a particular set of information, and then locate the area of the curve for that particular z-score, it is always on that table is calculating the area to the left of a particular z-score. So to find the area to the right of a z-score, you have to say 1 minus the area to the left of that particular z-score. Okay, so that's one thing you need to remember about z-scores and their tables. Okay, so in this first example I have, it says, all right, in this example, our first example in this one, it says find the area under the standard normal curve to the left of z equals negative 0.38. So let's look at the z table. Here we have negative values for z. We go down the columns and find negative negative 0.3. And then find the column that has 0.08 in it, find where those meet, and we have the area under the standard normal curve that is to the left of negative 0.38. So the area of that is the value that we found, 0.3520. Now, in this one it says, find the area under the standard normal curve to the right of z equals 1.25. So again, let's locate our z-score here, 1.2, and then go out 0.05 over here to find where they meet, and that is right here at 0.8944. But it is asking for to the right of the curve, so we have to use that complement rule and say 1 minus the area to the left of 1.25, and you get this right here. So take 1 minus the area you found to get our answer that is to the right of the curve. Now, if you're wanting to find areas under the curve that are between two z values, this is how you do it here. So if I'm wanting to find the area between these two numbers here, I take the area that is under my largest value and subtract it from the area of my least value. So that gets me this right here. These are the corresponding areas under each of these z-scores right here. Okay, so we could go back and find them on the table, but I think y'all are good now with finding things on the table. And there you go. The area between those two values there is going to be the 0.8445. Okay, so if you have a problem that says find the area to the left of a certain value, then what you need to do is convert the value of x to a z-score, and then use the table 5 to find the row and column that corresponds to the z, and then the area to the left of x will be the value in that row and column there given to you. Now, just to review a little bit more, it says to find, if your problem says find the area to the right of an x value, again, convert your x to a z-score, use the table, and then this z-score finds the area to the left. So this whole shaded region, well, the whole region in white here, it will give you. So what you do is say 1 minus that whole area, and that will find you this region over here that you are looking for. Lastly, if we have a problem that says find the area between two given x values, what you should do is convert your values of x, both of them, to z-scores, and then use the table 5 to find the areas to the left of z1 and the left of z2. And the area between z1 and z2 is the area to the left of z2 minus the area to the left of z1. And you've got your area that you're looking for those between values. Now, in an example I will do in a little bit, it deals with actually finding your x values. Instead of given the x value, find the calculate your z-score from that x value, and then look the z-score and its area under the curve using the table. Sometimes you have to work your way backwards. You are given a certain probability or proportion or percentile, and you don't necessarily have to draw the normal curve, but you will have to, on your table 5, find your proportion, probability, or percentile on the z-score table, the closest one possible, and then find your corresponding z-score that corresponds to the shaded region or probability or percentile. And then to obtain your normal value, use this formula right here to find x. So your x will equal your mean that you're given plus your z-score that you found that corresponds to the probability or percentile times, again, your standard deviation that you are also given. So this will be useful in an example that I will show you in just a bit. This example I'm going to show you, it's already worked out on this thing for you. Don't have to write anything in, but please write it down on your notes. I will work out another one alongside you here in just a little bit that deal with several questions. But this one, this example, it says the combined verbal and quantitative reasoning score on a GRE is normally distributed between, or with the mean, this right here, and standard deviation, this right here. What is the score of a student whose percentile rank is at the 85th percentile? Okay, so what we have to do here is this. The z-score that corresponds to the 85th percentile is the z-score such that the area under the standard curve, normal curve, that is to the left of 0.85. So what we would have to do is this right here. Let me pull up my z-table. It's right here. Here's my z-table. We are looking for 0.85. in this big old mess of numbers here. That's what your Z table is going to look like, is this right here. But as you go down, you can see all of your numbers getting bigger and bigger, getting closer and closer to the value that you are looking for. So let's look for 0.85. 0.85. This is the closest one right here that we are going to get to 0.85, and that corresponds to our Z value of 1.0 and then 0, 1, 2, 3, 4. So 0.04. You can see that is 0.04 right there. Okay, now let's go back to our slide here. So that is the reason why we came up with this Z-score right here, 1.04. Now, using this formula right here that I stated before, we're going to plug in our mean plus the Z-score times the standard deviation and come up with this right here. In interpretation, a person who scores the 1,246 score on a GRE would rank in the 85th percentile. So that's how you would go about it, working these Z-scores backwards. Now I have quite a large example for you here. I have parts A through I that we're going to go through together that all deal with this same given information here. It says the diameter of a ball bearing produced at a factory are approximately normally distributed. Suppose the mean diameter is 1.002 centimeters and the standard deviation is 0.006 centimeters. The product specifications require that the diameter of each ball bearing be between these values right here. And now, first part of the question, we're asked what proportion of ball bearing can be expected to have a diameter under 1.020 centimeters. So, what we need to do is, this is our given X value. We need to find the corresponding Z value by plugging it into this formula here. X minus our mean over our standard deviation. Okay, so we plug in 1.020 minus our mean, which is up here, and our standard deviation here. And do that calculation, and when we do, we get 3.0. And whenever we go to our Z table, let's go ahead and do that again. I'm going to go to the Z table. And look at 3.00. So 3.00 is this value right here, 0.9987. So that there is the value that we are looking for. It's the proportion of ball bearings that can be expected to have a diameter under our given X value. So this Z-score gives us this area right here. And that is our answer. Now it says what proportion of ball bearings can be expected to have a diameter over this given value. Now, since this is to the left and that is under, what is over is 1 minus the 0.9987, and that gives us 0.0013. And that is what we're looking for here. The area to the right of our given z value would be that number there. Okay, moving right along. Okay, it asks us here, it says what portion of ball bearings can be expected to have the diameter between 0.982 and 1.020. And then, so that, what this is asking is what proportion of ball bearings can be expected to meet the specifications that we are given from the beginning. Okay, we already calculated the z-score for this one and the area under the curve for that. So what we need to do is calculate this one and then subtract the two. So here we go. Calculate the z-score for this minus our mean divided by the standard deviation. And we get the value of negative 3.33. And if we go to our z-score table and find negative 3.33, we would end up finding its corresponding area under the curve, which is equal to 0.0012. And to find the area between these two given values, which is what we're asked to find, we would take our larger value, which was found here, take that area, and subtract our smaller area here. And get this new area here. And that is what we are looking for there for that portion. Okay, continuing on, part D asks us this. What is the probability that the diameter of a randomly selected ball bearing will be over 1.000 centimeters? So again, we take this x value that we're given and convert to a z-score. By using the mean and our standard deviation, we get this value here, negative 0.33. And then we go to our table and look up. I'm not going to do that, it takes too much time. We go to our corresponding table 5, and we get the area under that curve corresponding to that x value is 0.3, 0.3707. There you go. Now, the next one, we are asked to find, again, what is the probability, what is the probability that the diameter of a randomly selected ball bearing is under 0.995? So, hold on. The last one, it said over. So, over that amount, this is under 1, but over 1 centimeter, we'd have to subtract it from 1. So this would end up being our answer, 0.6293. So this right here is our solution for this one. Okay. Now, what is the probability that the diameter randomly selected ball bearing will be under this? So just like we did previously here, find the corresponding z-score. Take 0.995, subtract it from our mean, divide it by the standard deviation, and we get, what do we get? Negative 1.17. And it corresponds to this area right here on our z-tables. So 0.1210. Now let's look at another one. Hopefully y'all are getting the understanding the flow of all this happening now. These last two questions, or these parts F and G, ask us what is the percentile rank of a ball bearing that has diameter 0.991 centimeters. So what we do here is, again, look up or find our z-score according to the x value given to us, which is 0.991. Subtract it from our mean, divide by the standard deviation, whoops, 0.006, and we would get negative 1.83. And you look up that z-score on the table, and this is the area that you would get, 0.0336336. And so the percentile rank of the ball bearing, what you do is you change this decimal to a percent. So move the decimal place over to 2, and you get your percentiles are going to be whole numbers and nothing more than that. So it's going to be in a third percentile. Is where that ball bearing ranks for that amount, that diameter given to us. Okay, let's do this again, except with a different diameter. So our z-score, find it. And then that z-score ends up giving us 1.5. Look up the area under that z-score, and it gives us 0.9332. Oh, I meant 2, not 9. Now again, just change this to a whole number, move it 2 decimal places, and that is our percentile ranking. So 93 percentile. Okay, and then let's look at 2 more, I believe we have. Okay, part H, it is asking us to determine the 10th percentile of diameters of ball bearings. Okay, so 10th percentile, what we're going to do is look up the 10th percentile's corresponding z-score. So I'm actually going to do that on the table. So amongst these numbers here, we are looking for 0.10 or something very close to it. So let's go up to these negative values and actually go further down. Okay. So 0.10 looks like this is the closest number that we are going to get to that, and that is negative 1.2 I believe. 1.2, yeah, negative 1.28. So for the 10th percentile, corresponding z-score is equal to negative 1.28. And then if we use this formula here, we will find our ball bearing, or the diameters that we are looking for. Let's see. We are going to plug in our mean plus the z-score, and then their standard deviation, and that is equal to, kind of ran out of room here, and come up here, 0.9943, and that's centimeters. That's what that one is going to be measured in. So there you go. That is the diameter of ball bearings that is in the 10th percentile. Now we are asked to determine the diameter of ball bearings that make up the middle 99% of all diameters. That means we are looking for the 99%, the top 99%, and also the bottom 1%. Okay, and this will turn into the area under the curve that we have to find, which is 0.01, and then 0.99. We're going to look for its corresponding z-scores on the table, just like we did up here with that one. And when we do that, we get this z-score here. We get z equals negative, sorry, that was terrible, negative 2.32. And then on this one, we get a z-score of 2.33. So very close to one another, except one's negative, one's positive. And then use this formula right here to find its diameters we are looking for. So for this one, our x is going to equal the mean minus the, or plus, sorry, plus the corresponding z-score times the standard deviation, and that equals 0.988 centimeters. And then this one right here, our x value is going to equal to this. Which is 1.016 centimeters. So what this tells us is that our middle 99% of all diameters are going to be between these two values here, 0.988 and 1.016 centimeters. And there you go. That is, I think, all of, yep, that is all of section 7.2. and we will move on section 7.3. I'm thinking this one's going to be shorter. I hope so anyway, for y'all's sake. So I'll see y'all then whenever y'all return to watch 7.3.